Hi everyone. Welcome to our seminar on uniform pessimistic risk and optimal portfolio. Today, my name is Somaya Sadat. I'm the Assistant Director at the Center for Analytics and AI Engineering at the University of Toronto. And this is part of our joint seminar series with the University of Seoul in Korea. Along with my colleagues from the University of Seoul, it's my pleasure to welcome our speaker today, Professor Jong-June Jeon. Just a bit of introduction. Professor Jeon is an associate professor at the Department of Statistics at the University of Seoul. He worked in the Seoul Metropolitan Government as Director General of Statistics and Data from 2017 to 2018. He has researched asymptotic of penalized regression models and efficient computation algorithms for deep learning with quantile regression. Currently, his main interest is developing a generation model for machine learning with a causal, structural, and distributionally robust optimization for fast converging reinforcement learning. With this introduction, I'd like to ask Professor Jeon to please start his presentation.
Hello, everyone. Good morning, Seoul, and good evening, Toronto. My name is Jong-June Jeon. My talk is about making money with AI. Well, let me start with a well-known saying. Don't put your eggs in one basket. This is only one lesson from the Wall Street in my life. This is about risk diversification. Then first, before we talking about the risk diversification, we start with the well-known chart in stock price. Okay. This figure displays the prices of stocks. Amazon. As you know, the y-axis denotes the price of stock, and the x-axis denotes the time. If you are investor, maybe you are interested in the movement or trend of stock prices. If you invested the 6 months ago, then you lose money. But we are interested in the long term, the trend or the movement of stock prices. But we really, in short time investor, we are interested in the daily log return rate. So I will introduce the popular measure in the measuring the stock price as log return rate. Okay, the daily log return rate is defined by the logarithm of the ratio between the current price and the past price. Here, PT denotes the asset price at time t. Then XT is called the daily log return rate. If we assume the distribution of XT is stationary, then we have a chance to make a decision for the estimated distribution of XT. And here we are assuming that the XT has a stationary distribution. So we have to estimate the distribution of XT and make a decision based on the estimate distribution. Then suppose that we have two assets with the equal expected log return rate. Then which one do you choose? If you are rational and generally risk averse, you may choose the asset with low risk. That means the asset has a lower uncertainty with respect of prices. This is partially proved by the experiment. A general person choose the asset with low risk. So under this assumption, we make a better decision with respect to uncertainty. This is the key of the making a portfolio, optimal portfolio. The portfolio means literally is collection of assets. In a little mathematically, it is a weighted averaged assets. That the diversification is related to the return rate of the portfolio. That means by weighting the averaging of asset, we can reduce risk with preserving the expected log return rate of the portfolio. For a simple example, let me introduce the simple random variable following normal distribution. Here, you can see xj follows the normal distribution with mean mu j and the standard deviation sigma j. We are considering three assets following normal distribution, and that the three random variables may be correlated, and the portfolio is weighted average of the random variables. We denote the random variable of portfolio by y. As you know, the beta j is weight of the portfolio, and so the beta j has a positive value and its semantic is equal to B1. Then a natural approach to minimize the risk of the portfolio, then we have to define the risk of the portfolio. Here, I define the risk of the portfolio by a variance. Variance is an attribute of the distribution. It displays dispersion of the random quantities, so it is reasonable risk measure. Then the risk diversification is formulated by the following optimization problem. Here, I let a target expected log return rate be mu0 in real value, and we try to minimize the risk of the portfolio. That is, we try to minimize the variance of the return rate of the portfolio. So the optimization problem written as the minimization problem. You can see the objective function is written by the variance of the portfolio, and the constraint is written by the log return, the expected log return rate equal to be mu0, and the constraint of the weighted parameter. Okay, this is the risk diversifications of the risk factor, the variance. It is not well known that the Markowitz model. Okay, the minimization problem is the solving the Markowitz model based on the data. The modern portfolio theory is Markowitz model. That means the portfolio return is characterized by mean, and risk factor is represented by variance. If the investors are assumed to be compromised the balance between the return and risk, that try to minimize the risk under the constraint of log return rate. As you know that the Markowitz model is defined by the minimizing risk, the standard deviation of portfolio return. It is called sigma risk. There are very interesting the formulation of the optimization problem. I write the optimization problem more simply. You can see that the equation 1. And we consider there are P assets. I denote the random vector by X. And we assume the target return rate of our portfolio should be mu0. Of course, the mu0 must be a feasible set. And the Marquis model is formulated by the equation 1. It's simple. The minimizing the variance of portfolio with the constraint, the following constraint. Then we can very interesting formulation in next page. The variance is rewritten by the covariance structure, and the optimization problem is the size of the covariance with the constraint of mean return rate. Here, the sigma is the covariance matrix of X, and mu is mean vector. So if we try to the optimal portfolio, Marquis optimal portfolio, we have to estimate the covariance matrix of the asset prices. And if we have only the target mean vector, we always obtain the optimal portfolio by estimating the sigma and mu. And it is well known that this optimization problem can be solved by the quadratic programming. But there are many assets above the number of observation, then the estimation of covariance can be very unstable. So we have to considering the way to how to estimate covariance well, or how to estimate the mean vector of X. But in this presentation, we are not interested in the estimation of covariance matrix and the mean vector. But I want to point out the estimation of covariance matrix and mu is very important, especially under the circumstances of non-stationary situation. Okay. If we have a optimal Markowitz optimal portfolio, then we can vary the target return rate, and we obtain the optimal solution. By gathering the target return rate and the solution of the objective function, we can draw the efficient portfolio curve. Figure 3 displays the efficient frontier. Y-axis denote the constraint mu0, that is the target return rate, and x-axis denote the standard deviation of portfolio return. Then if the people are reasonable, then they choose the portfolio, the point above the efficient frontier. That is the Marquis model. Okay. Then we try to change the optimization problem by the following equation 3. Just we subtracting the constant by beta transpose x. This equation 3 is equal to the objective function. I mentioned before, the variance is invariant to the constant locational movement. Okay, then the the objective function in equation 3 can be written as the below. The variance can be converted the expectation of squared function because we have a constraint that the expectation of portfolio must be mu zero. So the 3 and the below equation is are equal. Note that the expectation of the scales is very similar to the risk minimization used in the regression problem. So the problem can be written as fitting a regression problem. In this situation, the response variable can be 0, and we are considering the constant coefficient and regression parameter minus beta. Okay, then our natural question is, if we change the loss function, the L2, scale the loss function with the other loss, how will the properties of portfolio change? We try to change the L2 loss or the scale loss by the quantile loss. The figure 4 displays the L2 loss and the quantile losses. Quantile loss is known as check functions, is non-differentiable at point 0. Okay. So I will talk about the optimal portfolio by minimizing quantile loss. Before the quantile risk, the optimal portfolio obtained by quantile loss, I'd like to talk about the alpha risk. The alpha risk is investigated by Bassett, Coenkel, and Kolas in 24. The equation 4 equation 4 is the definition of the alpha risk. First, G is a quantile function of y, and alpha is the value between 0 and 1. Then the alpha risk of y is defined by the integration of the quantile function g. Okay, if we are fixed alpha is B1, then the alpha risk is exactly equal to B1 minus the expectation of y. Okay, simple calculation. We define the y by a portfolio return. So minus expectation of y is a negative profit of the portfolio. So this alpha risk is a reasonable risk measure minus return rate. And if alpha is the value between 0 and 1, especially for continuous random variable y, the alpha risk is exactly same to be a conditional value at risk. That means minus expectation of y conditioning on y is less than alpha quantile level of y. So this is alpha risk. Then what is the relation between alpha risk, the quantile risk? The Bassett and Coenkel and Korudas show that the following proposition. Here we fix the expected return rate of y to be mu 0 and denote the quantile risk by alpha x. Then the minimum value with respect to beta 0 of the quantile risk is equal to the alpha risk up to constant. It is a very interesting equation. That means if we make a portfolio minimizing the quantile risk, then we can achieve the optimal portfolio minimizing the alpha risk. Alpha risk is well known. So we can always, the minimizing quantile risk, we can obtain the optimal portfolio with respect to alpha risk. So this relation is written by the equation 6. The left term is minimizing the quantile risk, and the right term denotes the minimizing the alpha risk. It is equivalent. So we have 3 short conclusions. The quantile loss derives a different optimality criterion of the portfolio risk. And the second is the optimality is the conditionally expected loss. That is the conditionally negative low return rate, and it is known as a pessimistic portfolio. Okay. Then the pessimistic portfolio is generalized defined base set. It's more general formulations. Simply, it is simply the pessimistic risk is an integration of the alpha risk. The equation 7 denotes the pessimistic risk is the integration of alpha risk with respect to some distribution defined on 0 and 1. So if we change the distribution bar phi defined on 0 and 1, we can construct various pessimistic risk. That means the pessimistic risk depends on the choice of the distribution defined on 0 and 1. And this distribution is called a distortion function. Then we can consider a discrete measure bar phi d point discrete point. Here we are assuming that the discrete measure has a point mass wk at each alpha k. Then the pessimistic risk is defined by the summation of the weighted alpha risk. And we can know that the minimizing the general pessimistic risk leads to the composite quantile regression. This is the same conclusion we have seen the previous slide, the relation between alpha risk and quantile regression. Okay, then we have 3 questions from the relation between the composite quantile regression and the general pessimistic risk. The first question is, what is the most pessimistic portfolio? What is most pessimistic means how we can choose the distribution of 0 and 1. How can we construct the most pessimistic portfolio? And this can be correctly defined. That means the most pessimistic, the terms of most pessimistic can be correctly defined, and if the proper definition, what is required, the condition, and that then it is possible, if it is possible, what the specific role of the value, the distribution these are our three questions. So we propose a new pessimistic risk by choosing the uniform distribution probability measure on 0 and 1. Then we call this new pessimistic risk the uniform pessimistic risk. It is defined by the equation 10. It's simple. The uniform pessimistic risk is uniformly integrated alpha risk. So we investigated the property of the uniform pessimistic risk by showing the limit of integrated alpha risk, a discrete measure. First, bar decay, let bar decay be a discrete uniform probability measure. On discrete point, we can show that the limit of the general pessimistic risk is equal to the uniform pessimistic risk. It is a simple result of Riemann integration. Okay, then we know that the uniform pessimistic risk is a very simple measure, limit of discrete pessimistic risk. And the next result is the uniform pessimistic risk is the limit of composite quantile risk. The uniform pessimistic risk is equivalent to the limit of composite quantile risk because we can conclude the same result of the minimization quantile risk, and it is related to the alpha risk. This result shown in equation 12. As we increasing k to infinity, the composite quantile risk converges to our uniform pessimistic risk. So we can relationship between the quantile risk and the UPL. So thus we can define the integrate quantile risk as a functional by equation 3. Please see that equation 13, the uniform pessimistic risk function with respect to G is a quantile function. It is written by the integration of the expected quantile risk, and G must be chosen as a risk function. So by choosing a small g, a quantile function, we can evaluate the risk functional. The equation 13 can be used, the M estimation can be used by the estimating quantile function. Okay, so we can obtain the following proposition 3. On the mild condition, the uniform pessimistic risk with respect to small g is larger than the true uniform pessimistic risk. That means by choosing small g, a quantile function, properly, we can achieve the true uniform pessimistic risk, and we can know that the g must be if the g is the true quantile function, the two terms are large g and large g, and the uniform pessimistic risk should be equal. So we can obtain the UPL, uniform pessimistic risk of y, by minimizing the proposed risk function with respect to a function g, where expectation y is fixed. That means by minimizing the risk functional, we can obtain true quantile function of y. So we can formulate the optimization problem for the pessimistic portfolio by the optimization problem can be written as the minimization problem. Here, the objective function denotes the UPR, and the constraint shows that the small g is a quantile function defined on 0 and 1. G is a quantile function, so G must be strictly increasing. Under this constraint, we have to minimize the UPR, but the function G is non-parametric. So we have to parameterize the function by some uh, element in functional family. We adopt a linear isotonic regression spline as follows in equation 14. It is the addition of the increasing function. Here, the Bm denotes the weight parameter, and D denotes the knot point. Note that the summation of Bm in equation 14 has positive values because G theta, here the isotonic regression, G theta must be increasing. We have some this inequality constraint. Anyway, we adopt this isotonic regression model. We can estimate the quantile function by minimizing the UPR. And we have the additional conclusion, the robustness of the UPR. It is known that the distributionally robust optimization, which is shown in proposition 4. Here, let Y is an element of the LP space and Z is an element of LQ space. And denote the CDF of the Z by Q. Then our UPR is the maximum risk of Z. As you know that the minus expectation minus profit is loss, and the UPL is equal to the maximum risk under the distribution can be changed under distribution Q. Note that Q is not the distribution we have seen in training sample space phase. That means in the test phase, the distribution can be changed. But if the distribution in test phase changes, we measure the supremum risk under the distributional shift. We minimize the risk. And the UPL is equal to the supremum risk caused by the distributional shift. Okay, so the proposition 4, the UPL is equivalent to worst case expectation in under the distribution shift. And we have 3 short conclusions. The pessimistic risk is a convex combination of alpha risk. And second, the pessimistic optimality is closely related to the minimization of maximum loss of the portfolio. And at last, the pessimistic optimal portfolio is theoretically robust to the distribution shift. We have 3 short conclusions of the pessimistic risk. Okay. Then we can extend the UPL by changing the distortion measure. Here, we introduced the beta distribution as a distortion measure. Here, B as H denotes the PDF of beta distribution measure, and the general, the UPL, can be written by the equation 15. We consider is larger than 0, H is larger than 0. And we can define the family of distribution here, M as H. Then we can show that the UPL is most pessimistic under this distribution family. So this is the answer I raised before last slide. What is the most pessimistic portfolio? Then the UPR is most pessimistic under this family distribution of family. Okay, the results shown in the theorem 4, we assume the y follows a generalized extreme value distribution, and we assume the distribution is included in the sum family, then the UPL is most pessimistic. Okay. Then we conduct a numerical experiment by with comparing the pessimistic portfolio. We considering COSPI 200 data set of daily log return rate consisting of 162 assets from 2010 to 2018. We evaluate the risk of the portfolio by the empirical UPR, alpha risk, return and Sharpe ratio. We're considering a benchmark portfolio, UPL, and the regularized UPL, the quantile regression, and composite quantile regression and Marquis model. And we evaluate the performance of portfolio by rolling samples estimation. The estimation schemes are displayed in figure 5. And as you expected, the UPR is the best performance, yes, in this situation. But we are focusing on why the UPR is the best. So we have investigated the trend, the price of stock, the trend of stock prices, and we found the phase with the high volatility in the stock prices. We monitoring the empirical UPL, alpha risk, return rate, and Sharpe ratio. We found there are some event in the stock prices 29th phase. In the 29th phase rolling period, we observed that difference in standard error, standard deviation in some stock prices detected in some and we investigate the risk in the phase. So the quantile level, estimated quantile level by the UPL, minimizing UPL and composite quantile regression, then the bias can be observed. And the Markowitz model can detect the any distributional change. So the UPL can effectively capture the quantile estimate, but the composite quantile regression fails to the behavioral tails of the quantile movement. So we conclude that the UPL can capture the change, or it can capture the change of the quantile levels, and it is robust to the distributional shift. And in numerical studies, the UPL is very good under the stock prices are very unstable. And it is interesting that this pessimistic risk can be applied reinforcement learning because the pessimistic risk tends to confront the worst case expectation. If we want to develop AIs to very, very efficient to learn in early stage, then it is useful to employ the pessimistic risk. Thank you for listening. It is my talk.
Thank you, Professor Jeon. This was a very interesting seminar. I'm sure everyone enjoyed that. I'd like to remind everyone, please, to type in any questions that you might have in the Q&A box, and we'll try to get them answered. Let's give it another minute in case anyone has any questions. Well, I guess it was very clear. That's great. Thanks a lot for the great seminar. I invite everyone to check out our website. We have another 2 seminars remaining in this series. Next Wednesday and Thursday, Toronto time, which would be Thursday and Friday, Korea time. And with that, thanks again on behalf of us at the University of Toronto and our colleagues at the University of Seoul for presenting in this seminar, and for those of you who attended, for attending this seminar. Thank you.
Thank you.